So we'll have the
Fine.
first talk now by
Yeah.
Pierre Ramond, tri- Tribimaximal mixing and asymmetric textures. So you can
Mhm.
start now. Yeah.
Yes. Okay. Good. So it's entitled From Electrical Engineering to Physics with Bow. Uh, when I went to Syracuse University, where Bow was, to learn general relativity with Peter Bergman. And my first advisor was George Sudarshan, who asked me before leaving for India on a sabbatical, is spin statistics valid for infinite component wave equations? Okay, and then he left. And then, so I had to read Streeter and Whiteman, and some of you must have read it, and the PCT spin and statistics and all that. And of course, I learned a lot about the edge of the wedge, but no progress. And then when Sudarshan came back, he told me that Todorov had found a counterexample for such an equation where the spin statistics doesn't work. There I was, completely adrift. Okay, and now comes the real chapter in my life, because in the light of it's dark here. I was rescued in the light of a new moon in the name of Professor Ayalam Balachandran. He was encouraging. He was helpful. He wrote, when he was away, he wrote precise instructions in extremely detailed letters. And his thesis was very simple. Can you go from the S to the T channel through the Mandelstam triangle? Now, some of you may not know what the Mandelstam triangle is, but you will have to learn. It's a triangle. And it basically, the mathematical structure in there is the appel Campé de Ferrier orthogonal polynomials. And I managed to, as a result, it did not really work, because when you leave the S channel to go into the Mandelstam triangle, it's okay. But if you want to get into the T channel, you get into a cut right away, and you can't do anything. It doesn't really help. But nevertheless, it was good training. And with Bill Manx, a fellow graduate student, and Jean Neutz, we wrote 3 papers, which were enough to get me to secure a late postdoc with a laboratory, the National Accelerator Laboratory, now known as Fermilab. Now, but Bao did more for me, because he managed to get me a 3-month stay at Abdul Salam's ICTP in Trieste, which was a wonderful gesture, because there my horizons opened. I was able to get out of the Mandelstam triangle, and I met Jean Neutz, because with whom I collaborated, but I never met, and Hirotaka Sugawara, who introduced me to what became the string model, duality. Okay? And so that is the history. Now, let us go to the next thing. So I noticed from the title of the talks at Balfest, most of them are really very, very mathematical, and mine is not too mathematical, but I want to let you know about a real problem in neutrino physics, and I want to present what we have done, and there it goes. So there is, as you know, a Yukawa breakdown of the quark-lepton gauge coupling patterns. I mean, the quarks and leptons have the same gauge couplings, basically, okay? But except, of course, for color. But there is something very funny, namely that they are 2 large angles. So therefore, whereas for the quarks, the mixing angles are very small, at most 12 or 13 degrees. So the lepton mixing matrix, which goes under the name of PMNS now, after a Italo-Russian and 3 Japanese, is a product of 2 matrices, and I'm going to take the second matrix, the U of TBM, which is a beautiful matrix with an ugly name. The name is Tribimaximal. And this is it. So it's full of beautiful numbers like square root of 2/3, square root of 3s, and stuff like that. And this was invented by actually Don Perkins, who passed away a month and a half ago, I guess, was a great experimentalist at Oxford. And once he saw that the measurements for two of the mixing angles were large, but also very close to square roots, etc., I think they basically decided this is how it looks. Now, okay, so this particular matrix, if you look at it by itself, they do give you two large atmospheric and solar mixing angles, but there is no reactor angle. Okay, and a reactor angle means that you have a bunch of reactors, and you basically look at the neutrinos coming out of a nuclear reactor, and it's really a short baseline. But anyway, at that time there wasn't any, and people were kind of happy. And but something very interesting, of course, is that the U-1 originates in electroweak charged lepton Yukawa matrix. It originates in electroweak sector, okay, namely the charged lepton Yukawa matrix. So whereas the other one, we don't know where it's coming from. And the question is, does U-1 have enough Cabibbo-Hayes to get a non-zero value for the reactor angle? And this is the kind of stuff. So in other words, we called it Cabibbo-Hayes because this is coming from the Cabibbo sector, okay? And therefore, we called it the Cabibbo-Hayes. But since the Tribimaximal gives no reactor angle, all the experimental value of the reactor angle must come from this. Now, why do we insist on that? Well, as every physicist know, Dirac never ceases to impress people, and Dirac says when something is beautiful, you should go after it, basically. And the question is that the TBM looks like some nice structure. Maybe it's a reflection of some nice structure in the ultraviolet, and therefore that is why we work so hard to make it work. Okay, thank you. Next slide. So to give you an example of the standard kind of model that comes about, is a very old model from 1979 based on SU5 grain unification by Howard Georgia and Cecilia Yarskog. And what happens, the three Yukawa matrices that come in the standard model, charge -1, charge 2/3, charge -1/3, okay, are all symmetric. This was the assumption. And then you have a bunch of gut scale relations from SU5, which goes as follow. The tau lepton is equal to the bottom quark, which of course is is actually in the ultraviolet. Mu is 3 times ms, strange, Me is 1/3 of MD, so that the determinant of the -1/3 is equal to the determinant of 1, etc. And this is beautiful, okay? And what SU5 says is that the -1/3 Yukawa is somewhat related or very close to the transpose of the -1 Yukawa, okay? In the case of these people, of Georgi and Yarskog, they assume that the y-1 is symmetric. However, this gives you a problem, because if this is true, you find that U-1, okay, is almost like the CKM matrix. In other words, all the angles in U-1 are at most Cabibbo size, okay? And there is only one difference, which is a difference having to do with the 2-2 element of this matrix C. And this is what it does. You don't have to know the details. But what is the point that is very troublesome, okay, is that now you can say in this kind of model, what is the size that you get? Well, so you work it out, okay? And what happens is that you find that the reactor angle you get is about 4 degrees, okay? Well, that's too bad because the physical value is about 8 degrees, okay? So therefore, it looks like this example is kind of a normal example for this SU5 thing. But therefore, that means this beautiful TBM mixing is dead. Okay, so next, please. Next slide. Okay, so the question is that since it is very beautiful, can it be saved? Okay, so the problem here is that leave TBM alone, but U minus 1 and CKM and U of the CKM quark sector matrix are closely related. And in SU5, as we just said, okay, this is the minus 1/3 Y and the charge minus 1 Yukawa are related by transposition. But the question is that the assumption that these people have made was that the transpose of Y minus 1 is the same. I mean, it's a symmetric matrix. So what we decided to do was to drop the assumption of the symmetry of the Yukawa matrices. Okay, this is a bunch of paper, and we assume what Feynman used to call damn the torpedoes and let's calculate, and then if it works, we'll worry about how to make it work. How to make sense of it. So we invented this particular set of matrices. You don't have to know the details, okay? But you see that in Y minus 1/3, the 1,3 and the 3,1 elements are not symmetric, okay? That is basically the only difference. And you see the 1 minus 1 is here, you see, you take the transpose and you just change the thing in the middle. You see the C to the minus 3. Okay? A little bit lower, please. Can I see the rest? Thank you. Okay. So and all these coefficients are what's known as Wolfenstein parameters. Okay. So this is the result. Okay. So now we calculate, and what happens is the theta 1, 2. Okay, it's one of the angles, okay, is actually not so good. It's about 6 degrees above PDG. PDG means the particle data group, right, at the Lawrence lab. The other one, okay, is about 3 degrees below the PDG, so well above its 3 sigma. And the reactor angle, as you can see, overshoots the PDG. Okay, the reactor, I mean the Diabet and Reno values, okay, are basically smaller than this. So now we have a problem, okay, and because now we have overshot it, okay, but we are theorists. So next slide, please. Okay, salvation. So the question is that suppose we add a phase to the tribimaximal, okay? So that means the tribimaximal, you saw all the entries were real, and we're gonna add a phase to it and see what happens, okay? Well, the beautiful thing that happens is that when you do that, the prediction for the reactor angle is altered by a phase. And you see that basically that lowers the overshoot because e to the I delta absolute values, it's only cosines and sines, etc., etc. Okay, and so what do we do? Can I lower the slide? Thank you. So what do? I set theta reactor at the PDG, okay, and that gives me the phase. All right. Now the phase goes in the literature as called the delta CP, and we get plus or minus 1.32 pi. The global fits, but global fits don't mean very much because they are there is no direct observability in the data yet, but these are global fits. You can see it is very close. That was a big surprise to us, okay? But the second most interesting surprise is that the atmospheric and solar angle shift. They also shift, but they shift to within half a degree of their PDG values. Okay, so this is that is basically an amazing thing. All right, so okay, so this is the end of the damn the torpedoes thing. The parameters of the Yukawa matrices, etc. We have to try to understand what the relation among them is. But right now, okay, this asymmetric matrix, okay, or texture, okay, has a definite prediction, which is that it doesn't give you the sign, because in the absolute value, the sign of delta does not matter, but it gives you the magnitude, and if the magnitude is observed to be close to what the global fits are, we're in business. Okay, so therefore, we have to work harder. Okay, next slide, please. Okay. All right. Okay, now comes the ugly part. Okay, so this is a purely phenomenological analysis that we did. Okay, it's a bit more than phenomenology, because we have our texture satisfies the CKM matrix, the ultraviolet values, the determinants of y-1 equals to the determinant of y-1/3, etc., etc. Okay, so everything looks good, except we are left with one prediction. Okay, and basically which is the delta CP value. Okay, and we are left also within 1 sigma of the particle data group values for the solar and atmospheric angles. So okay, so now we went on and they said, okay, we have to do something about it. Namely, we have to go and build a model so as to understand exactly what goes on there, because maybe this texture may be telling you something about basically this mysterious sector of the standard model. So the ingredients are the chiral fields, the regular SU5 stuff. In the model, there's no tree-level electroweak Yukawa coupling, therefore all have to come from messengers. The vector-like fermion messengers, which of course couple to standard model mycelium. So that looks a lot like what people nowadays are in love with effective field theory, but effective field theory has been with us since Fermi. Now, and then we have to add a bunch of objects which are called familons, okay, which only have family group charges, okay? So now these are the ingredients. And now I'm a model builder. Can I please lower the move the slide a little bit? Okay, so we have to find a particular family symmetry. Okay, this is the semi-direct product of Z13 by Z3. It's okay. It has different triplet representations for the three families, actually. Okay, and it is interesting because it has two inequivalent triplets, which enable you to actually single out the lack of symmetry of the matrix, because that way you can single out by group theory a particular element, the 1,3 element versus the 3,1 element, for example. Okay, and for those of you who like group theory, this group is it's a subgroup of a modular group, PSL213, which is itself a subgroup of G2, and G2 as a discrete subgroup, but also as a continuous group. Okay, so next, please. Okay. Now, so the assignment that reproduces the texture, the chiral matter family charges have, of course, a family symmetry, and therefore there's the 5 bar is along the 3-1 of the family symmetry, and the 10 is along the 3-2. This is what works. The electroweak breaking Higgs fields are, they are singlets under the family symmetry. And then we've got a whole slew of vector-like messengers, okay? And that's not necessarily very interesting, but in our papers, you found that that with those messengers, you can generate a great deal. You can, for example, find the determinant relation in a natural way, okay? So it has a lot of very neat little things, which, of course, if you're not in this field, you're just closing your eyes and get another cup of coffee. But it is basically what it is. And now there are, of course, okay, can you please put, thank you. There are these things, the bunch of familons, which have no standard model or SU5 quantum numbers, but they do have the quantum numbers of the family symmetry. The fascinating thing about this model is that the vacua of these things, in order to make it work, because these things will get a vacuum expectation value. When they get a vacuum expectation value, then you get the texture, okay? But it's very complicated to get the potential that gives that. But look at that, all of them are very simple configurations. In other words, the components of because they are triplets, components of these things are a bunch of zeros and one, okay? And whatever fine tuning we have is basically is the fine tuning, if you want, is mapped into the vacuum configuration. And then, of course, the vacuum configuration will have to be looked at, but this is as far as we go with this. So this is more or less, I think, where we are. Yeah. Okay. Now, of course, we have to add the neutrinos. Okay, because now we want to go back to TBM and see whether or not. So this was the part without the neutrino, and of course, okay, I'm forced to talk about the seesaw neutrinos, which means that SO10. Why? Because SO10, okay, which is greater than SU5 cross U1, right? The 16 is a 5 bar plus 10 plus a 1, okay? And that's it. Then there is the vector 1 is 5 plus 5 bar, etc. Okay? And therefore, what happens is that you have to look at this in some ways like this. So SU5 cross T13, there's the 10, so the 16, this was the SU5 stuff, going to SO10 cross T13, and you see what happens, and the 16 is in a 3-2, and the 10, which is the vector, right, goes into this one, and it's the same content because you can have a vector-like coupling, okay, between one and the other. In other words, the 16, you see, has a 5 bar in it, the 10 has a 5, and they can marry, get a mass, and then you get back to SU5. Okay, so that's it. Now, we have 3 right-handed stereo neutrinos transforming this way, okay? And we have 1 familon coupling to the stereos, namely the N bar. This is to make one of the ingredients of the seesaw. And then we have a familon phi sub m, and which transform as a 1-3. And now the thing that okay, can I please have the move a little bit? The thing that is completely remarkable, okay, is that in a vacuum, which is 1 minus 1, 1, okay, now there's a phase into the I pi in it, okay? It's a little bit different, okay? But you find that this is diagonalized by TBM. Okay, this is quite remarkable. And the diagonal and the eigenvalues are 1 minus 1/2 and 1 over some scale, all right? So that is quite amazing that TBM becomes important, right? With a relatively simple vacuum structure. Okay, so all right. So now let us go back. Let us go seesaw mechanism, right? Excuse me. S is D 1 over M. M is the Majorana mass for the stereo neutrinos, transpose. D is a Dirac mass. Again, we have to add a familon, okay, which transform this way. And this is the vacuum, okay? And at that point, S, if there is that vacuum, then D is such that S can be diagonalized by TBM. This is how this is treated. And therefore, what we have here, okay, is fundamentally a diagonalization of S, okay, by TBM. And therefore, we do have, this thing reproduces the structure of the lepton mixing matrix with a U minus 1 times U of TBM, okay? And now we got to start find out what it, and so we're so happy, etc., etc. And then we go and read out the light neutrino masses. Now, one of them, M of nu 3, is twice. By the way, the phase doesn't matter in this case for the fermion masses. M nu 3 is twice this, but there's a little problem. Remember, there's a 1. Remember, there is a degenerate eigenvalue, right? 1 and 1. That means that M, the mass of nu 1, the mass of nu 3 are the same. There is no such thing as nu 1, nu 3 oscillations. Okay? So it doesn't work. So why am I boring you with this? Okay? So we have to go further. Is there a fourth right-handed neutrino? Okay? All right, if there's another neutrino or something like that, okay. So now, for those of you who know my work, I mean, if you look with the standard model and you go with SU5, this is okay, and then you go to SO10. Now SO10, Howard Georgi on the one hand and Fritsch and Minkowski on the other hand went there, and then Glashow and Georgi say, wait a minute, SU5 is easier. And then Feza-Gurset, Pierre Sitivi, and I, we went to E6 because that is the road to exceptional groups, right? In other words, the Dinkin actually tells you that. So as a good theorist, I said, why not look at E6? Well, you see, in E6, the fundamental representation of E6, which is 27, is a 16 of SO10 plus a 10, and then there's a little 1 in there, okay? So there is one more degree of freedom. So we look at now at PSL 213. Okay, so now we say maybe we should look at this, and we notice that this modular group 213 has contains a complex septet, okay, which is the 3-1 plus a 3-2 plus a 1 prime. Remember the representations of that group. There was a 3-1, a 3-2, a 1 prime, and then a singlet, and a 1 prime. Those were all complex, and then a real singlet. Okay, and therefore we have to find a way to, can we marry E6, okay, this guy, with PSL 213? All right, okay, so we are going to, now we know that we need to give to these guys, the 16 and the 10 and the 1, some T7 quantum numbers, okay? And therefore, we are going to basically, excuse me, I'm looking at my, yeah. Thank you, good. So what do? Well, somehow there must be a way to couple the 7 of PSL 213, we don't know what it is, together with E6, okay, such that the 16 picks up a 3-2, the 10 picks up a 3-1, and the 1 picks up a 1 prime. And there is your fourth neutrino, stereo neutrino. Okay? All right? So I'm almost finished. So now let me, I will not say much more, but so if we do this, our S, the script S that we had before, as another contribution, this object times this. This is, of course, has this one has 2 zero eigenvalues, etc. And we find that there is a way that actually is not in contradiction with experiment. Okay, but what it is this. So we get basically that using the existing oscillation experiments, which of course give you the absolute value of the differences of masses. mu1 is 27.6 millielectron volts. mu2 is 28.9, and mu3 is twice that much. So that means the splitting between 1 and 2 is relatively small, but the splitting with mu3 is large, okay? And that means we are in a normal ordering of the neutrinos. And therefore, notice that 2 here is that so now this is a definite prediction, which is interesting. If the mass of the heaviest neutrino is twice the mass of the next lightest neutrino, that would be a kind of well, it will be a very big feather in the hat of these models. But you see what kind of desperation we are in. We have this pattern that has broken, okay, and we don't know what to do with it. So we have to invent models. And the only thing that is tangible right now is that we have definite predictions, but at what cost? What I'm very interested what I'm very interested here in is the fact that we have to go up the ladder. I mean, if we want a fourth neutrino, for example, the natural way is to go up to E6. This is a natural way of introducing. Just like the natural way of introducing the seesaw was to go from SU5 to SO10. And I like patterns, etc. So this is it. I finish with my last slide. Okay. And my last slide is for the birthday professor. Okay, and I mean the following thing, that without Bal, I would have been forced to go back to engineering. They had offered me jobs at engineering in Bell Labs and stuff like that. But I'm forever thankful, because he saved me from engineering, which enabled me to pursue physics and all the beauties of the natural world, and getting paid for it. So Bal, I wish you a happy birthday. I am very honored to have spoken in your fest, and I wish you the very best. Thank you.
Okay, I just wanted to greet you. I'm very happy you're here, and I hope that you'll continue on your trailblazing path. And I hope you'll keep meeting once in a while. Okay.
Yes. I'm sorry. I retired last summer, so I will. I think at some point I will join the room 316.
That would be great. And you can also talk to us. Talk to us on your work.
Oh, sure.
We'll be
sure.
And
yeah.
Your family.
Yeah, I should give you a plug. I should give you my work over the last few years. This work is a little bit older, but my work has been to trace the genius of Yoichiro Nambu, and Lars Brink and I I've been writing a book. Unfortunately, Lars passed away a few months ago, but I'm finishing it.
Lars passed away?
Oh, yes.
I did not know.
Yeah. So he had cancer, and so, but we did not finish the book together, but I'm finishing it now. And then I think it will be an interesting book, because it is a mixture of the history and also trying to explain the physics of what Nambu was doing, which and we learn a great deal from it. I think people will enjoy it, and especially today people are going very, very much into well, they're very much swayed by fashion. But it's interesting to see a genius at work who basically comes with an imperfect model, which is the right model eventually. In other words, that basically doesn't give up, and it's wonderful. So this is what I've been busy at, so anyway, that is one thing. Yes, but I love to speak in your meeting, and my interest right now is on the Ising model. So maybe that will be more interest to your audience. Okay. Anyway, Bao, thank you so much.
But you were looking at SO10, E6, and so on. So the values you get obviously have to be run down to low energy using the renormalization group.
Mm-hmm. Yes.
When you say M nu 3 is twice M nu and so on, do you expect this to hold eventually?
Well, it's not. Yeah, I mean there is a little bit of change, but I mean it's not as violent as the. Yes, indeed, but it's not as violent as the values of the masses certainly change, but again, it's mostly weak interactions. Okay, it's not like strong corrections. It's not like the factor of 3 between MB and M tau. Yes, I do expect it to change. We haven't really looked at that. We were kind of lucky just to find TBM in there, whereas in fact we had not put it in. Yeah. Yes, indeed. It's a good point. It's true.
Sorry, presumably your sterile neutrinos are supposed to represent dark matter.
Oh no, I don't know anything about that. I don't know what it is. I mean, I've not looked into them being a dark matter. I mean, they are just.
It would be the natural candidate.
They could be, but we certainly have not explored that. Yeah. I mean, so the singlet may be more interesting. The fourth neutrino may be more interesting.
Do you have a constraint on the masses of the sterile neutrinos? This 1/m matrix?
Yeah, we do. I did not. Yes, there is. Yeah. And in fact, one of my collaborators in studying leptogenesis, you know that these things are Yanagida and company, basically suggested that actually in the decay of those right-handed neutrinos, you would essentially have CP violation, yes, and therefore, since B minus L is conserved, then it will transmute itself into barrier number violation, etc. And yes, and the mass of these right-handed neutrinos are very crucial to this. And I think the jury is still out because it's a very complicated subject.
Thank you, Pierre Ramond.